So we were looking at the governing equations, and we realized that there is no point in really looking for an exact solution. And then we figured out that we would actually start looking at a mean quantity like mean pressure, mean velocity, and so on. But then we also found that the mean quantities actually don't satisfy the governing equations. That's where we ended up. Okay, so that was the point, and therefore the fact that we realized was that we need to go to another framework. We can't just proceed the way we have been doing it for laminar flow. Okay, we can do that, but before we do that, I need you to introduce you to this term called turbulent stress. And to do that, we need to look at the equation where we stopped last time. We will see what is turbulent stress in that equation, and then we will see how to attack turbulent flow problems. Is that clear? Okay. So can you all look at the equation that we left last time for the mean flow in let's say x direction? So we use just u for the x component of velocity, right? Is this right? This is what we had. Yeah, and we realized that those terms that I have written on the right hand side, which actually contained the primed variables. So the primed variables are the fluctuating parts of the velocity field. Okay, u prime, v prime, w prime are respectively the fluctuating velocities in x, y, and z direction, and they gave rise to certain quantities, right? Those quantities are extra terms that have come up in the mean flow governing equation. And we said that's actually a complication, and therefore we can't really solve for the mean quantity. We need to know what these fluctuations are. So there's a nicer way to write these fluctuations, and that's what we are going to do first. Let's say we want to, so we are looking at incompressible fluid. Okay, we are going to look at rho being constant. So rho is a constant. Let's see what is del by del x of u prime plus u prime v prime plus u prime w prime. Sorry, we don't want that. Plus del by del y of u prime v prime plus del by del z of u prime w prime is. Okay, I'm just trying to look at a quantity, okay, which I have looked at as products of the fluctuating components, and I'm taking some derivatives. I want to connect that expression to the first expression that I have written. So this is, and I'm going to simply apply the product rule. So that will give me u prime dou u prime by dou x plus again u prime dou u prime by dou x plus u prime dou v prime by dou y plus v prime dou u prime by dou y plus u prime dou w prime by dou z plus w prime dou u prime by dou z. Just expanded the products, and if you look at terms this and that, okay, that's nothing but u prime into dou u prime by dou x plus dou v prime by dou y plus dou w prime by dou z plus the other quantity that we have is u prime dou u prime by dou x plus v prime dou u prime by dou y plus w prime dou u prime by dou z. Oh, I have written all these things wrong. Is this correct now? So that's what we must have derived the last class. Okay, so the why I want to do this is because what is this? That's 0, and how do we know that's 0? We are talking about the fluctuating components, but we know that the mean quantities and fluctuating quantities separately satisfy the continuity equation. We proved it in the last class. Okay, so therefore this quantity is 0, and therefore what I have on the left hand side is same as what I have on the right hand side. But if you look at these quantities on the right hand side, this is what I actually have inside the integral in all these three terms. Is that right? Or in other words, what my intention is to write down this quantity in the square bracket with this particular one, this particular quantity I want to substitute and use there. That's the idea. Should I say anything? Should I explain again? Yes, no? So that's a no. Okay. So then I'm going to substitute the quantity that I have circled. Dou u bar by dou t plus u bar dot grad u equal to minus dou p by dou x plus mu. The Laplacian, okay, the Laplacian of u, I'm going to write it in terms of components. Write different components. Del square u by del x square plus mu del square u by del y square plus mu del square u by del z square minus, okay, the quantity that's inside the integral del by del x of rho u prime square bar minus del by del y of rho u prime v prime bar minus del by del z of rho u prime w prime bar. What have I done? So look at the quantities that are inside the square bracket. Okay, so the quantities that are inside the square bracket, I am replacing it with this general expression that I have circled. Okay, so this is, that's because we found that the quantities are same, the one which I have circled and the quantity that is inside the square bracket. Okay, but each of those quantities are integrated from 0 to t and divided by t. So by definition they are all average quantities. So I have put basically average of each of them. So the first is del by del x of u prime square. So that's just del by del x of rho u prime square bar. Okay, it's basically the mean quantity. So not mean quantity, it's the mean of the fluctuations or mean of the square of the fluctuation. So of course you know that that's not 0. We talked about it last time. So that's why you get all these non-zero quantities on the right hand side. Okay. Is equal to, I'm going to combine now, let's say that and that is minus dou p bar by dou x plus del by del x of mu dou u by dou x minus rho u prime square averaged. I'm going to combine that and that. to get plus del by del y of mu dou u by dou y minus rho u prime v prime averaged. I'm going to combine that and that to get plus del by del z of mu dou u by dou z minus rho u prime w prime averaged. That's okay? Okay. So, yeah, so I was just going to ask you what is that quantity mu dou u by dou x? That's tau, right? So that is basically we defined a constitutive relation. So originally we had the tau itself in the governing equation. Then we used Newton's law of viscosity and replaced that tau with mu dou u by dou y or mu dou u by dou x, whichever. Okay, so that's how these terms that you have gotten. Okay, so those are stresses that's really associated with the viscous mechanism, right? Those are the viscous stresses. Okay. Now, what we are saying is that effectively, if you look at the equation for the mean flow, it's not viscous stresses alone, but there is something else also that's appearing along with those stresses. Okay, right? Because each of them contain, so the first stress actually contains something extra here. The second one also contains something extra. Third one also contains something extra. So that extra stress is known as turbulent stress. Okay, so it's the stress that's coming because the flow field itself is fluctuating. So that's what gives rise to what you call as the turbulent stress. Okay, so every place where you actually had the stress, you could say that, okay, there are two stresses. One is coming from viscosity, another is coming from the fact that the fluid field is fluctuating. Is that clear? Okay. So remember now, when you derived the Cauchy's equation, right, you actually had the stress, you did not know what to do then. So you said, okay, we will make use of Newton's law of viscosity, and therefore you converted that stress into velocity and proceeded. So you get everything in terms of velocity, and therefore you were able to solve the equations. Now you have actually ended up with a similar situation where there are quantities which are these primed variables which you do not know. Okay, and therefore what we need is something like Newton's law of viscosity. Okay, in other words, we need an expression for the turbulent stress. Okay, so that's the way people have been thinking about these terms, and people try to derive various terms. None of them are as good as what Newton's law does. Okay, so we still do not know what is the best way to do it. There are various approaches. So for example, when you look at people talking about turbulent flow and how they solve it, they will also tell what kind of a turbulent model that they have used. Okay, so that's what generally or really the field of turbulence modeling. So it's really an unsolved problem. We don't know what is the best equation that we want to do. Okay, we want to replace these fluctuating quantities with some mean values, but we really don't know what is the best thing to do. But therefore, there are certain models that you would use when you really want to solve a flow problem. So if you think, you can contribute, maybe this is one of the area that you should think about. What is the best way to replace those fluctuating quantities, or is this split up of mean versus fluctuation itself is the right way to do it? Okay. Anyway, so that's what I wanted to say about turbulent stresses. Now, realizing that we can't take this route, okay, we are basically going to use a bit of non-dimensional analysis, some insights from the experiments, and then try to come up with expressions and quantities that we can use in our usual design routine. Okay.